Hello, this is lesson 5.6. Here we will look at some applications to exponential and logarithmic functions. So the main application to these functions is modeling growth or decay, right? So we have a model, say p of t, a function of t, that equals some number p naught times e to the kt, right? Now, this can be used to model how fast things grow or decay, things like chemicals or so like how fast a chemical decays, or say how fast a population grows. Okay, so the number p naught is the initial amount. K is the growth rate. Right, if k is a positive number, it's growing. K is a negative number, then we have a decay model. And then t is usually just time. Okay. So, for an example, say in the year 2012, the population of a city was 5.99 million. The exponential growth rate was 1.28%. Okay, if we know this bit of information, then we can model the population. So we can make a model of the population by p of t equals the initial amount times e to the k t. Now notice that I wrote the rate as a decimal and not as the percentage, right? So, 1% is equal to 0.01, right? 100% is equal to 1 in a decimal form. So like 99% is equal to the decimal 0.99. So we have to be comfortable using the conversion between percentage and decimals in this section. So 1.28% is equal to 0.0128. You just move the decimal over twice. Okay, now this will give us the population of the city in millions. This was 5.99 million. Okay, so for example, if we want to know the population in the year 2018, well, how do we do that? Well, you have to be careful. This model starts at 2012. So 2018 is 6 years later. So since this was in terms of years, we will just plug in a 6, and that will represent the year 2018, because 6 years plus 2012 would be 2018. So plugging in a 6, we get 5.99 e to the 0.0128 times 6. If you put that into a calculator, you'd get about 6.5. And remember, this is in terms of millions for this question. Okay. What if we ask ourselves the following question? When will the population equal 9 million? Well, if we want to find the time at which the population is 9 million, we just set p of t equal to 9 and then solve for t. So we have p of t, we set it equal to 9, and we solve for t. That will give us the time at which the population is 9 million. So we divide and get e to the 0.0128d equals 9 over 5.99. Okay, and now we have to take the logarithm of both sides. So if we take the logarithm of both sides, we get logarithm and the e cancel out. We could bring the exponent down. So we get 0.0128 t equals log 9 over 5.99. And we are solving for t, so t will equal log 9, 5.99 divided by 0.0128. If you put that into a calculator, you should get something like 31.8 years. But it's 31.8 years after our starting point. Remember, this model started at the year 2021. Or 2012, excuse me. Now let's think about the time at which it takes for the population to double. Right, so we call that the doubling time. A doubling time is just the time, say capital T, such that the initial population times e to the kt will equal twice of the initial population. And so if you set your model to equal twice the initial population and solve for time, we call that the doubling time. So in our model, we have 5.99 e to the 0.0128 t. We want to solve for the doubling time. Well, this is pretty nice because we can divide both sides by 5.99 and that number goes away. Right, so we just have e to the 0.0128 t equals 2. Okay, we take the log of both sides. These logs cancel and get 0.0128 t equals log 2. So t will equal log 2 for 0.0128. Okay, and that is about 54.2 years. So in 54.2 years, the population will double. Okay. Now similarly, if a model is decaying, we could find the half-life is what we call it, the time in which half of your substance decays. So say, for example, let's look at a new example. We are looking at decay, a decay model. Say we have some substance and it is decaying. Say we model it by its initial amount, E, and then it will be a negative rate, say negative 0.01 5.4.1 t, right? So this is a decay model. Now if we want to find the half-life, what that means is we find the time such that the model, so I just picked a rate there, we couldn't use any negative rate, but anyway, such that the model equals half of what we started with. We could divide the initial amount out. So in this example, we just take the log of both sides. So when we take the log of both sides, we get the rate negative 0.01551 t. I should use a big T. Let me use a big T. Because I used a big T here, so use a big T. So anyways, we take the log of both sides and we get this. Right, if I just take the log of both sides, then we can pull the exponent down and we come up with this equation. So solving for t, you have log of 1/2 divided by the rate. So we come up with this is the answer. You could put that in a calculator at home if you wish. Should be about 44.6 or something. But anyways, for a doubling time, we found that it was just log 2 divided by your growth rate. And for a half-life, we found it's log of 1/2 divided by the growth rate. So that should work, right? So you could use these formulas if you wish to find the doubling time or the half-life of a exponential model. Okay, and let me just do a quick graph here. So this is e to the k t for positive k. If you flip it, you get e to the kt for a negative k. Right, so this is decaying, this is growing. Right, so populations grow in this manner, and then things that decay exponentially, they decay like that. Things like radioactive substances can decay, for example. That you can measure it and work out how old it is and stuff using these formulas. Anyways, that ends today's lesson about applications of exponential modeling. Thank